Hi everyone, I am Shashidhar. I am one of the TA for this NPTEL course on atom probe tomography. So today we will be showing live demonstration on how to load the samples in the atom probe and how to acquire the data from the atom probe. So here we are seeing LEAP 5000 XR, relatively new generation of an atom probe. This XR represents the reflectron which professor was explaining to you, which can increase our efficiency of. So now I'll show you the individual parts of the atom probe on the whole. So here what we see is a load lock chamber. This is the first entry into the atom probe instrument. Here we have different carousels which we will be seeing later on. The next part is our buffer chamber. So initially the samples which you load in load lock chamber, after they reach a required level of vacuum, we transfer them to our buffer. So this is the buffer chamber in which we transfer the samples from the load lock chamber, and this transfer is done through this transfer rod. And this transfer rod is also used to transfer our chambers from the buffer chamber. This puck is transferred to analysis chamber. So we see 4 different camera views of the analysis chamber over here. So this will be the typical puck which we transfer, and you can see this is the LEAP electrode, and we place the puck just before the LEAP electrode and bring the tip into the view of the LEAP electrode for doing the final acquisition, which we will be seeing later on. So this, as we see, is our analysis chamber, and now we see the most important part of the APT, the laser. This is the laser source which we are using for running our samples. Now I'll show the loading of the puck into the carousel which is taken from load lock. Now I have taken out the carousel from load lock. Now I am removing this puck and loading into the carousel. Now I'll take this carousel and load back in the load block. What we are seeing now is the loading of the puck into the analysis chamber from the cameras fit inside the analysis chamber. Now we are done with the loading of the samples into the APT. Now what we see from now is the acquisition part of the data. Now before acquiring the data, we have to align the samples with the local electrode. What we see in the right bottom window is the local electrode. You can see a cone-shaped object. This is the local electrode. And what you see in the left top window is my puck. As you can see, I am aligning the center of this puck with the center of the cone-shaped object in the left top window. Now, you can see in the left bottom window that I'll try to bring this puck closer and closer to this local electrode. Once I see something in the field of view of the local electrode in the right top window, then you can see some bright spots patterned bright spots in this right top window, which are nothing but our tips. So now I'll try to bring these sharpened like bright spots before the local electrode. Now I'll try to move this puck slightly upwards and then bring these sharpened lines right in front of the cone-shaped local electrode. You can see I'm doing that. So these what we are right now using are pre-sharpened silicon tips, which are usually used for alignment purpose. So all the acquisition we do today are on these pre-sharpened silicon tips. You can see that I'm moving the puck such that finally I'll bring these bright lines in front of the right in front of the local electrode. So once this is done, you can see some tips came into the field of view of the local electrode in the right bottom window. So now I'll align this tip right in front of the local electrode. I'll center it and then I'll try to focus these tips. So focusing is nothing but just bringing this tip into the sharpest possible contrast using the fine adjustments. You can see that I'm making some movements to center the tip, and then I'll use plus and minus adjustments, nothing but focusing to bring the tip to the sharpest contrast. So once these basic steps of aligning my tip, since we are done with the alignment of the APT tip with the local electrode, now we'll focus on the acquisition part. What we are seeing on our screen is the main acquisition control window of APT. As professor was mentioning throughout his course, there are two basic modes of acquisition in APT. One is laser mode and the other one is voltage mode. As on today, we'll just focus on voltage mode of acquisition. So I'll move my window and you can see that I have kept two windows on my screen. So the left window is the AP suite window, which shows live data as it's getting acquired. And the right window is the main acquisition control window. You can see I have changed the mode of acquisition to voltage. And you can see just below that various parameters of voltage mode. Specimen temperature, specimen voltage, detection rate, pulse fraction, pulse rate. So initially, to get a feel of what all these windows show as we acquire, let us acquire some data. So I'll start the acquisition and I'll increase the specimen voltage. So as we have studied in this course that for the atoms to get evaporated, they need a certain voltage for field evaporation depending on what's the tip radius, what is the nature of atom, etc., etc. So now I am increasing the voltage of the specimen so that till the point where I can achieve some field evaporation. So now towards the left, you can see some purple dots popping up. So this circular maps are nothing but detector event maps. So whenever some atoms get detected hit the detectors, these purple dots pop up. And towards the bottom, what you see is counts versus mass to charge state ratio. This is mass spectrum. So I am increasing my voltage and seeing for the atoms to get detected. You can see now that a peak has appeared in mass spectrum as well as a bunch of purple dots have appeared, which means some atoms are getting field evaporated and getting detected on the detector. So now, since we have got a feel of acquisition, what we'll try to do is to just increase the speed of our acquisition, I'll try to change the detection rate to 0.5. Okay, before that, since I know that these tips are silicon, I have zoomed in the mass spectrum to around 14 and 28, because this is where the silicon peaks are expected. So you can see that near 14, you can see some peaks appearing, which indicates that silicon atoms are getting field evaporated and getting detected. So now, to slightly make our process faster, let me increase the detection rate to 0.5. Okay, so now, right now we are running the samples in voltage mode. Now let us try to understand the effect of pulse fraction on the voltage data acquired in the voltage mode. So right now we are using a pulse fraction of 20%. Okay, let some data get acquired, and we'll see. We can see the peak again appearing at 14. I have reset the detector event map as well as mass spectrum. So this data is got collected already at 20 pulse fraction. Now you can see just beside the acquisition parameters, there is a blue color window in which you can see single events, multiple events, and background. So the background, typical background which we are getting at 20 pulse fraction is around 7 ppm per nanosecond, which is quite high. Single events acquired are 91%, and multiple events are 8.2%. Okay, just remember these values for the purpose of comparison. As we increase the pulse fraction, we'll see what happens. So now I'm stopping the acquisition. Now I'll try to slightly increase the pulse fraction to 40%, and we'll see what happens. Okay, and I'm putting all the other parameters constant. I have just increased the pulse fraction from 20% to 40%. And again, you can see the atoms getting popped up on the detector. You can see these detector events getting increased, as well as you can see the peak also getting popped up in the mass spectrum. Now, if you can observe that there is a significant reduction in this background. Earlier, in case of 20 pulse fraction, we could see around 7 to 6 ppm per nanosecond of background. Now you can see 2 ppm per second of nanosecond of background. So there is significant decrease in background, which means our signal is improved with increase in pulse fraction. Now you can see the single events as well has slightly increased. Earlier it was around 91%. Now it has increased slightly by 1 or 2%. And multiple events also, which was around 8%, has slightly decreased. So which means our data has slightly improved. So as we change the pulse fraction, we could see that background has decreased and slightly our single events has increased and multiple events have decreased. And you can see okay, let us stop the acquisition over here. And now let us try to change the pulse fraction to 60 and see what happens.
Okay, I'm starting the acquisition again at 60 pulse fraction with all the other parameters constant. Okay, you can see the atoms getting popped up on the detector. And the peak also appeared at 14 in the mass spectrum. Okay, now you can see as I increase the pulse fraction further to 60%, you can see the background has further reduced to 2 ppm per nanosecond. And the single events and multiple events also are slightly improved compared to that of 20%. You can see the peaks are also getting clearly resolved in this case. So more or less, we have understood the effect of pulse fraction. So as we increase the pulse fraction, we are seeing better signal. We are seeing background is getting lesser, which means our data gets improved. Multiple events are getting less. What are multiple events? Okay, let us stop this equation and further increase the pulse fraction to 80%. Okay, now I have increased the pulse fraction to 80%. So the effect is more or less similar to what we have seen earlier. Background has reduced and the multiple events reduced, single events have increased, which means as we increase the pulse fraction in the voltage mode, our signal gets better and better. So we have briefly seen the effect of pulse fraction on the data acquired in the voltage mode. So as I am today, we can end the acquisition thing, and in the next video, we'll try to focus on the acquisition in the laser mode.